Mostly when you have a thesis from railway, you want to be in time. Railway is mostly defamed in Europe for being late, delayed. So we try to start within 3 minutes plus minus, plus always, not minus. So we are in almost time. First of all, I would like to welcome you all, especially the guest who has traveled from international guests, committee members, friends and relatives, parents of Mikael, and also industry representative. Thomas is sitting, I saw. LKB, who has been a sponsor of the project. My name is Uday Kumar. I am head of the subject and also chairman of these proceedings here. Thesis has been supervised by Professor P.O. Larsen-Kroik. I have been co-supervisor all the way without active participation. My participation has been to be in the meetings and all, but mostly Professor P.O. Larsen-Kroik has been the in charge. Thomas has made contributions through the discussions and all. Thesis deals with condition-based maintenance for effective and efficient rolling stock. So thesis focuses on the maintenance issues. How can maintenance of rolling stock can be developed, further improved so that capacity can be assured. So even though the thesis deals with the rolling stocks, its more focus is on the maintenance issues, condition monitoring and all. Mikael is a, if I remember your industrial economy, Vegovatten, I don't know how to translate, industrial engineering with a civil engineering focus. He joined 2009, January, you told me. I thought you started, we had interviewed you in 2008, but formally he started 2009, January. And during the last 5 years, he has been working on this topic. He has written many papers. You have the thesis, those who have not got the thesis. So copy of the thesis is available on the table, so you can kindly collect it. Formalities. I will start with, I will be introducing shortly the committee. Prior to that, I will introduce how to go forward. Mikael will be presenting 25 minutes to 35 minutes, approximately, his thesis. Then I will request the opponent for half an hour, 1 hour, approximately. It's a recommended time, and then the committee member, 20 minutes, 15 minutes, depending on the time. Then it will be open for the audience to ask questions. Now I will introduce the opponent, Professor Doug Hargreaves from Queensland University of Technology. You are a mechanical engineer working with, I have met him earlier some 6-7 years ago. I don't remember, around approximately. He has been earlier here. And he has an interest in this tribology, the research area, if I remember, but quite long interest in this condition monitoring and all. A committee member, we start with Professor Srividya. She is from Indian Institute of Technology, Bombay, India. Currently visiting faculty at Haugesund University College in Norway. She is a civil engineer, and fortunately or unfortunately for you, it is a reliability, structural reliability. I don't know, it is good or bad, we'll see. Secondly, Professor Sebastian Stichel. He is the vehicle dynamic. He is the head of or director of KTH Railway Research Center, or Railway Janway Group, you call it. I don't know why you call yourself group. It's a group. And he is also a specialist in vehicle area, vehicle dynamics. And he has worked in Bombardier and all. And Mikael, it will be very interesting to get Sebastian's opinion about your thesis and all. Is very much aligned to what you are discussing, at least the object of your study. So that will be very interesting. And thanks, you could agree to be in the committee. And last but not the least, Professor Bjarne Bergqvist. He's in a short, we call it like an internal candidate in the committee, but usually they are the representative of the faculty board. If you do too bad or too good, they may report. And so, but he has, his specialization is, you'll be looking to the data, how data has been analyzed. So we have very balanced group of committee here. And most of questions will be, for you, they'll be directly to you in their own area of specialization. I will now request Mikael to, I don't know whether I have forgot one more thing. After the meetings, usually committee will retire to a room to discuss whether Mikael should get the grade, pass or fail. It's only 2 grades. And after that, 2 o'clock, there is some coffee and all. I think, Mikael, you should ready and you should try to present for 30 minutes approximately your thesis. 25, 30. I gave you a big band actually. You work with the statistics, 25 to 35 minutes. So anywhere is acceptable. Please, Mikael.
So, thank you, Mr. Chairman. I am here today to present my thesis titled Condition-Based Maintenance for Effective and Efficient Rolling Stock Capacity Assurance. It is a study on heavy haul transports in Sweden. Today's presentation will include introduction. We'll go with the thesis approach, research methodology. Then we'll go into the result and discussion, and with conclusions and scope for future work. Starting with introduction. The railway system consists of track, we have rolling stock, and we have power supply. The track consists of straight and curved sections, and we have switches and crossings. We have the rails. There are different rail profiles, and we have different widths between the rails. The rolling stock consists of locomotives and wagons. These might have powered or non-powered wheel sets. We have different loads and speeds, and the wheels might have different profiles or diameters. The focus in this research is on the interaction between wheel and rail, and this will be used for capacity assurance of the rolling stock using condition-based maintenance. Maintenance is a combination of all technical and administrative actions intended to keep an item in or restore it to a stage in which it can perform a required function. Maintenance can be either preventive or corrective. Preventive maintenance is made before the failure, and corrective is made after the failure occurs. Preventive maintenance can be planned for and downtime minimized, and corrective maintenance usually do not have enough time for planning. The preventive maintenance is either scheduled or condition-based. A scheduled or time-based maintenance uses fixed interval between the maintenance actions, an action taken regardless of the condition of the item, while condition-based maintenance uses condition monitoring to know when to perform the maintenance action. The condition of an item degrades over time. When the condition reaches a failure level, predetermined failure level, a maintenance action is performed and this function is restored. Over time, the condition does not reach the original state, and it will also be less time between the maintenance actions. The condition monitoring in this research have been performed either by using manual measurements or automatic wayside stations. The condition monitoring tools are the mini-proof wheel measuring equipment. We have the automatic wheel profiling station, and we have the research station measuring wheel rail forces. A decision support system contains thresholds for safe and economical use. For example, see the failure level in the graph. When an asset reaches this specified level, a decision for action is made. Trending of data or information is another way to reach this decision, and that could be, for example, using prognostics. The iron ore transport line in Northern Europe goes from Luleå in Sweden to Narvik in Norway. It's about 550 kilometers long, and the axle load is 30 metric tons. We have several different kinds of trains on this line, and they differ on speed, load, length, and if it's freight or passenger trains. The largest amounts of trains are from LKAB Mining Company, and they are transporting iron ore. These iron ore mines are situated outside of Kiruna and Gällivare. And in 2012, 26.3 million gross tons of iron ore was transported, and 20% of these was shipped out of Luleå harbor. The wayside measuring stations used in this research are situated just outside of Luleå. On the top here we have the automatic wheel profiling station, measuring all wheels passing using cameras and lasers. In the bottom one we have the research station, and it's measuring wheel rail forces in a curve situated in a curve of 408 meters of radius, and it's using strain gauges attached to the web of the rail. The iron wagon you can see here is a Fanu wagon, and it's been in traffic since 2005. They travel in trains consisting of 68 wagons behind the locomotive. And then the loaded speed is 60 kilometers an hour, and you have a 30-ton axle load. The Fanu wagons always travel in pairs, and the master wagon is containing the brake control system. And they are connected at the A end via a steel rod. They will always be master and slave. The designation will keep, regardless of travel direction. In the picture you can also see the bogie and axle designations. The yearly travel distance is between 120 and 140,000 kilometers, and the wagons are visually inspected after each loading before they are allowed to leave the train yard. So if anything looks wrong, they stay there. They're also subjected to a workshop review between 1 and 2 times a year, and this preventive maintenance strategy is based on the travel distance. Now we'll go into the Thesis approach. In the railway industry, the capacity of the rolling stock is a measure of the railway's overall capacity. Scheduled or time-based maintenance is a very simple maintenance strategy, but capacities can still be reduced due to failures. With the gradual loss of function, a condition-based maintenance strategy is possible, and then the reduction in capacity can be minimized. The most expensive component of a freight wagon that need periodic replacement is the wheel, and most failure modes for a railway wheel have a gradual loss of function. The main purpose of this research is to develop an approach and methodology for assessing the current state of a railway wagon wheel, and suggest a prognostic model for effective maintenance planning leading to capacity assurance. There are 2 research questions stated in this thesis. The first one is, how can condition-based maintenance facilitate capacity assurance for rolling stock? The second is, how does information about the state or health of the item affect the planning and execution of railway maintenance? In the table you can see how the research questions are linked with the papers appended, and at the bottom there is a list of the appended papers. The scope of this research is limited to maintenance issues of rolling stock, focusing on maintenance management and condition-based maintenance strategies. There are some limitations in this research, and it's only heavy haul wagons in northern Sweden that are used. We're only looking at the iron ore wagons from LKAB Mining Company, of the wheels of the wagons. Only condition-based maintenance and condition monitoring methodologies. The measurement data is from several different sources, but restricted to wayside stations, manual measurements, and maintenance data. And we're only using the data-driven models. Now I'll present the research methodology used. This is the research methodology I have been using, which can also be seen as the 3 key steps of condition-based maintenance. Starting with data collection, I collected profile data. I have the manual measurements from the mini-proof measuring equipment. I have the automatic measurements from the wheel profile station. And we also have the reprofiling data from the maintenance workshop. The force data is from the research station. Here it's also possible to get the data from the infrastructure manager, Trafikverket. And then we have the maintenance data from LKAB computerized maintenance management system. And then the reprofiling data from the maintenance workshop is one input. In the processing and analysis step, I've started with putting all the data into a common format, and then I've done a data cleaning using standards and manuals, a literature review, and expert information. Then I've done an exploratory analysis, and the next step is doing a detailed analysis of the data, turning it into information for decision making. In the decision support step, it is seen as the collecting of several different kinds of analysis information and combine them into decision support tools. Now let's go into the more interesting parts of the results and discussions. I will start with the wheel profile. And in this figure you see the wheel profile, which is a cross-section of the wheel and the wheel that is in contact with the rail. The solid line is a new wheel, and the dashed line is a heavily worn wheel. When you're reprofiling, you have to remove material by a turning machine to get a clean cut of the profile. Doing that is equivalent to putting a new solid line underneath the dashed line, and then you would see how much material had to be removed. Other reasons for reprofiling are wheel damage, such as rolling contact fatigue, out-of-run wheels, or wheel flats. Indicated here are 4 standardized profile parameters, and they're used by both measuring systems. SH is the flange height, SD is the flange thickness or flange width, QR is the flange angle or gradient, and TH is the tread hollow wear. We also have 2 main parts of the wheel profile. We have the flange marked in red and the tread marked in blue. These results are from the automatic wheel profiling station. On the x-axis you have the parameter measure, and on the y-axis is the density. This data is for 14 days of April and August of 2013. And for this time periods, a total of 104,000 axles were captured. About 46,000 of these travel in the loaded direction, and about 10,000 of those were missing data. This is a relatively small data sample, but it's here to show the capabilities of the automatic profiling station. Now we'll go into details about the different graphs. I will start with the flange height. The safety limit for this one is 36 millimeters. And now you can see that we have a larger amount of wheels, closer to 28, which is a new profile. And it's especially so for August. This might be due to seasonal differences, lubrication that is put up here, or a recent maintenance strategy. If you go in for the flange width, we can see that we have a similar shape in the densities. None of them seem to be indicate that we are close to the safety limit at 22 millimeters. And this similar shape is also apparent in flange gradient. Here the safety limit is 6 millimeters. Going for the flange gradient, or the tread hollow wear, the safety limit is 2 millimeters. And as can be seen in this graph, most wheels are very close to 0. This is good, since that means we are using the whole tread line of the wheel while trafficking the line. It's not just a narrow band that we're using. So we're using the whole tread line, and that's good for both the infrastructure and the wheels. So this data that's coming is from the vertical and lateral forces from the research station. The vertical forces are positive in the downward direction, and the lateral forces are positive outwards in the curve. There are 2 positions of the wheel axle. On the wheel axle we have the inner wheel, which is the inside of the curve, and the outer wheel, which is outside of the curve. Here I'm presenting an exploratory analysis of 14 days of January, April, and August of 2013. Totally about 220,000 rows of data is collected for this time period, and half of them traveled in the loaded direction. We have 3 measurements for each wheel passing, since there are 3 measurement points, and these are all collected into one bunch, so that's why it might seem a bit more than for the wheel profiles. Now we'll go into detail, looking at the vertical force for the inner wheel. Here we can see that the forces are centered just below 150 kilonewtons. This is good since that is half of the allowed axle load. And it is same for the vertical force for the outer wheel, also centered just below 150 kilonewtons. Looking at the lateral forces, starting with the inner wheel. In January, we have a big difference between the forces. It's not a unified data set. We have forces at -50 and +50. To me, this looks like some kind of bad steering, possibly due to snow and ice helping the wheel get caught in a unwanted angle. In April, looks good, and in August, it looks lower. This might be due to the trackside lubrication of the whole line, or that the top of rail friction modifier station that was installed in June of 2013 just prior to this measurement point. Looking at the lateral forces for the outer wheel, there are similar forces for January and April, and in August it is lower. Same thing might be due to the top of rail friction modifier just installed prior to this, which has helps a lot to reduce the lateral forces of the wheels. So now I'll present my maintenance management framework that is developed through all the experiences that I've had in my research time here. Starting with designing for maintenance, you have to start with the stakeholder input of the different component properties of the vehicle. These components are then assembled into a vehicle with, for example, specified wheel or brake properties. The maintenance policy contains condition monitoring, vehicle configuration, and workshop locations. In a condition-based maintenance strategy, the condition of the vehicle or the components need to be monitored. The workshop location dictates the need for spare parts or transportation. And the company organization, the maintenance policy, and the infrastructure configuration are all parts of the maintenance management. And of these, infrastructure configuration is the one that is the most difficult to control, but it still plays a major role in the need for maintenance for the railway wagon wheels. So this graph shows the life length of several wheel discs. The data is collected from the computerized maintenance management system of LKAB. And these wheels have been in traffic for up to 7 years in order to collect this data set. The wheel diameter is calculated 70 millimeters from the back of the flange. And the diameter is what dictates the life length of the wheels. Now we're going to describe one wheel. Starting with the natural wear, we have about 240,000 kilometers of natural wear before we have a maintenance action. And we have a very short stint of natural wear before the next maintenance action of reprofiling. Then we'll have about 80, maybe 90,000 kilometers of natural wear before the last maintenance action of reprofiling this wheel. Then we have a larger stint of maybe 250,000 kilometers of natural wear. Unfortunately, we don't know exactly at what diameter this wheel was taken out of traffic, since no measurement was performed on the wheel before it was sent for re-wheeling. Looking at this graph and calculating all the natural wear, we have I've come up with 3 millimeters of natural wear for every 100,000 kilometers of travel distance. Looking to find a golden wheel, the best performing wheel possible, you would use 400,000 kilometers of natural wear, and then you would remove 8 millimeters of the diameter at reprofiling. And this would correspond to the total travel distance of 1.2 million kilometers. With the yearly travel distance of today of 120,000 kilometers, that would mean about 10 years of service. Wheel damage is one of the major reasons for a wheel being reprofiled early. Costs associated with wheel maintenance are estimated as a total cost of maintaining a wheel axle, adding up the costs for wheel turning, downtime due to wheel turning, which is a loss of operation, we have the manual inspections, risk of wheel failure or derailment, and then replacement of worn out wheels. In order to make these calculations, a set of assumptions have been made. And the first one is that wheel failure distribution can be modeled as a variable distribution, seen in equation 1. And then the wheel set degradation can be modeled as equation 2. Now we'll go into the conclusions and scope for future work. Conclusions for the first research question: how can condition-based maintenance facilitate capacity assurance for rolling stock? Condition monitoring data supports effective maintenance planning. It performs the assessment of the state of the item and facilitates correct decision-making regarding maintenance actions. This assures the reliability and availability of the rolling stock. Condition-based maintenance decisions are made based on real-time data from wayside condition monitoring stations. Combine this with life cycle cost analysis to facilitate the achievement of planned rolling stock capacity. Conclusions for the second research question: how does information about the state or health of the item affect the planning and execution of railway maintenance? Railway operation in colder environmental conditions increase the natural wear rate of the wheels. Seasonal trending of the wheels or wheel performance data need to be considered when planning maintenance actions. The continuous monitoring of lateral forces on the vehicle can decrease the risk of derailment. A large lateral force and insufficient friction could make a wheel continue to travel in a straight line instead of following the curve. This would lead to abnormal wear or possibly even a derailment. The data collected from condition monitoring and transformed into information will provide an improved prognostic estimation for this asset. These decisions will lead to efficient and effective maintenance planning and execution of maintenance tasks, which in turn will lead to rolling stock capacity assurance. My research contributions, I believe, are application of condition monitoring technologies and condition-based maintenance strategies for rolling stock, and this enhances the effectiveness and efficiency of maintenance actions. Maintenance management framework for rolling stock, and an improved theoretical life cycle cost model. Scope for future research: combine the data-driven model with physics of failure models for a hybrid model to use in future maintenance assessment. Develop dynamic decision support system for the optimal strategy to use existing condition monitoring tools to plan and assess the wagon maintenance. And also subjecting these findings to other parts of the wagon or rolling stock in general. Thanks for listening.
Thank you, Mikael, for at least